Okay, so we're gonna go ahead and let's go ahead and start where we left off. So, rules for doing atomic orbits. Number one, H is always gonna be a 1s when you're writing its atomic orbit. All other atoms count the number of electron-rich regions, and you'll put that as its atomic orbit. So since, for instance, carbon right here, we have 1, 2, 3 electron-rich regions, which goes to sp2, and that is what its atomic orbit is. Pi bonds are all made with p orbits. So 2p is going to be for your double bonds, and 3p will be for your triple bonds. So let's go ahead and answer this question. So it's saying that which of the following are the correct orbits that make up the pi bond and the sigma bonds between the carbon atoms? So between the carbon atoms, you have a double bond. That double bond is going to be a sigma bond and a pi bond. Remember, double bonds have one sigma bond and one pi bond. So we're going to make the correct atomic orbits go with bonds. Okay? So let's go ahead and start with pi bond. So the pi bond says pi bonds are always made with p orbits, 2p or 3p. So since it's a double bond, we're going to do pi, 2p, 2p. One for each carbon in the bond. Then we have sigma. So we also have a sigma bond. And so for sigma bonds, we're going to count the number of electron-rich regions of each carbon, like we did earlier. 1, 2, 3 electron-rich regions. So that's going to give us a hybridization of sp2. So our sigma will be sp2. And then the other carbon is also sp2 as well. So that gives us the answer of A. Once you practice this a little bit more, it'll get a lot easier. So for magnetic orbitals, you're gonna have to memorize this. Okay, so for all elements on the periodic table, lithium through nitrogen, you're gonna use this pattern. For oxygen through fluorine, you're going to use this pattern. Okay, so we'll have to just do a bunch of memorization sheets over those. So like there's questions that are just dealing with the order that these numbers go in, like 1s with the star. So the star indicates a higher energy anti-bonding, and so on. It's pretty easy to memorize by knowing the order. 1s, 2s, 2p. And know that the star version comes after the lower energy level. So considering the following molecular orbital diagram, what are the names of the labeled orbitals A, B, and C? So A. So this looks like a molecular orbital diagram from lithium to nitrogen. So A would be that sigma 2p with the little asterisk on it. And then B would be pi 2p. So that knocks out the bottom. And then C is going to be sigma 2s. And we have to pay attention that it is the non-asterisk one. So B would be our answer for that question. Okay, so now with fluid structures, you're going to be able to calculate what we call the bond order, which is going to be the number of bonds that you get between a molecule by using what we just did in the molecular orbital diagram interpretation. So you're going to basically do the amount of electrons in each of them, like how we would do with the molecular orbital diagrams. Same thing, follow the rules, Hans, Pauli, Aufbau. Go in the order up and place your electrons going up, and so on. Then you're going to calculate the number of electrons in the antibonding molecular orbitals. So that's going to be the ones that are like with the asterisks, minus the number of electrons in bonding molecular orbitals, so the ones without the asterisks, and divide that number by 2, and you get how many bonds are between your diatomic element. But there is a much easier way to do this. So I'm not even going to freak you out and put you through that frustration of calculating that using the molecular orbital diagrams. You could just use this little table. So bond order the easy way. So all you have to do is memorize this table. Even just the first 2 parts. Okay? The number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20.